computing or computer science, which is a very young discipline. You know, the foundations can be set around 36. The first computers appeared used in defense applications. In the 70s, you had the advent of the mainframes, commercial applications. In the 80s, you had the convergence between computing and telecommunications, which opened the way, web and internet. And then there are other important landmarks. What I'm going to say here is that we are living a revolution that is overwhelmingly exploding. And there are many other landmarks here, the Internet of Things, cloud computing, multiple systems. So this is a real revolution, very spectacular. And today we have systems everywhere. We have hundreds of videos of systems that provide services, isolated services that we would like to integrate to produce global services. And these computing systems are hidden in appliances, devices of any kind. Okay, the last introductory slide to say that today all the big IT companies, like say Google, for instance, or IBM, they don't sell isolated hardware or software or services. They sell systems which are integrating hardware and software. And they have a very global vision. Google is not only interested in services, and interested in mobile phones, in cars, healthcare. And here you see a revision by IBM. What they say, they want a smart planet, systems everywhere, and these systems are instrumented. You have sensors everywhere, so you can sense the state of almost everything. You have interconnectivity, different many ways to interact between people, between machines. And finally, a strong request is intelligence. We want systems to be intelligent. Why? Because we want to use all the system infrastructure to make predictions, to control the use of resources, and this is a strong demand, intelligence. Now, a very significant trend is that the interest in computing has moved over the past decades from programs to systems. And I hope you make the difference. A program computes just a function. It's, a program is a piece of software, computes a function, and it has these characteristics you see here. I'm not going to comment on this. Transforms some input value to output value. It's terminating, it has predictable behavior, it's deterministic, it has a behavior that is platform independent. On the contrary, what I call a system is composed of hardware and software, is interacting continuously with the physical environment, and in order to understand its behavior, we have to see it as a relation between input and output streams. It's non-terminating. All systems are non-terminating in principle, and they have non-predictable behavior. The behavior is platform dependent, and we have no theory to deal with system design. This is something I'm going to explain. So, initially we've been interested in writing software and programs, and now we want to develop systems, and for this we have no theory. So, this slide explains further the concept of system, and here I'm saying that systems are hard to design, not because, of course, they can also make a complex computation and handle complex data, but the important fact is that they interact with some possibly complex environment. You see here, when we have resources, buildings, transport systems, telecommunications, health. And what counts here is this interaction between the system and the environment. And the dynamics of this interaction depend on the characteristics of the computing platform. So we are living a revolution and we are reaching a turning point, a breaking point, where we are, so the breaking point is that we break with traditional computing systems engineering and so what I call traditional computing systems engineering is the technology we have in your laptop, in servers, and we are interested in systems that jointly meet several technical requirements such as reactivity, that is responding within bounded time. For instance, a flight controller should respond within guaranteed bounds, which is not the case for your laptop. Systems must be autonomous. Autonomy means many things. For instance, no manual start. If you have, for instance, embedded systems in your car, if there is a problem, you cannot have access, direct access to the electronic components of your car. And of course, another is power management. In all mobile devices, the software that is developed there is not developed as the software of your laptop. Why? Because programmers take care take care of the resource management. Okay? So we are using different programming techniques. And of course, we have another list, a long list of requirements here. And in addition to that, we have economic requirements because, for instance, embedded systems are used in mass market products. And here, you don't try to develop the best possible system. You are seeking some economic optimum. And needless to say that today we have no theory for building systems of guaranteed functionality and quality at acceptable cost. So let me talk about system design very quickly. Because design is something very important in computing, in computer science. Of course, design is a universal concept. It's the process that leads from requirements. The requirements express needs, express desires to artifacts. So perhaps I'm an artist, I am a civil engineer, electrical engineer. I will design systems. And so this is an example that shows that when you design an artifact, you have to solve two hard problems. One is how to translate the requirements here, I'm talking about an API, into a program, into a recipe. Okay? This is the proceduralization step. And then once you have the recipe, you decide to choose the resources and to have a materialization of the art. Okay? And these are two important steps and that need some intelligence, some human intervention, of course. Cannot be carried out automatically. I mean, of course, here you can do that automatically. I mean, at least going from here to here, this has been invented by a human. And it's important also to notice that for the same recipe, you may have different implementations. Okay, may have different qualities of cake. Now, for systems, you follow a similar process. You start from requirements that are declarative. Usually, they come from analysis, some logic. They are not executed. And then the result of that proceduralization step is the application software that is executed. And then you have another process that allows, leads through code generation to some implementation. This is the system. And here, of course, an important concern is what? Correctness. Are we doing things correctly? Whether what we get meets the initial requirements. And this is something very, very important. Then it should be guaranteed or partially guaranteed by any system design process. Now, an interesting question is where we are standing today. Today, in systems engineering, we have, say, two schools. We develop two types of systems that are difficult to integrate. Either critical systems that whose development costs a lot of low complexity, and here I'm giving some examples of critical systems, and complex best effort systems. So for best effort systems like large telecommunication systems, web-based applications, the main concern is not, is to have, of course, granted some minimal system availability, but the main concern is how to manage the resources efficiently. And for the future, what we would like to have is affordable critical systems, so cheaper technologies for critical systems. Because there are many application areas like transport, health, energy management, where we need critical technologies, but for the moment they cost a lot. And the second demand is that we should be able to integrate, to put together, to make cooperate critical and less critical systems. So let me give you an example. Understand this today. We have systems producing critical services. We have banking systems that are handling confidential data, for instance, and we have telecommunication systems. We would like, for instance, to use your mobile phone to access to confidential files. This may have some, this may be a risk operation. So why? Because the telecommunication systems are not secure enough. And furthermore, when you are interacting, a best effort system is interacting with a critical system, the critical system may be attacked or infected by a less secure system. So today, this is a kind of dream, this is a kind of vision. People are talking about Internet of Things, intelligent transport systems, smart grids, ambient intelligence. Or here the idea is that we will be using the IP protocol in the Internet to integrate services provided by embedded systems. And the idea is that embedded systems will be interacting autonomously through the Internet. This is a very nice vision, but it's dangerous also, you can imagine this. And for the moment, this is not attainable because, as you probably know, the Internet infrastructure is not secure enough. So what's the situation today in systems engineering? I think this is, it's worthwhile thinking about that. We have well-established engineering disciplines, like, for instance, civil engineering, where civil engineers can build bridges like this one. So they have the theory to do that. They write down systems of differential equations, whatever. This is provided by theory. And they know how to build bridges that will not collapse for centuries, with a very high probability. While in computing systems, we don't have predictability, we don't have constructivity, what I call constructivity results. We have, of course, theory algorithms, we have architectures, but we don't have a theory about how to combine many different algorithms, architectures, how to build systems out of components. This is something I'm going to explain. Now, in order to understand more precisely where we are standing today, let's consider the concept of system correctness. So, I said that the system is correct if it meets its requirements, and requirements can be classified in two categories. You have transportness requirements, and transportness requirements, what means transportness requirements means that the system will behave as expected despite different kinds of problems that can appear. For instance, hardware failures, design errors, disturbances from environment because systems are interactive, and of course malvoluntations. Okay, so if you are considering pure hardware or pure software systems, you don't have all. I mean, for pure hardware systems, you have this. For pure software systems, you have this and a bit of this. But if you consider the system as the composition of hardware and software, you have all these possible sources of problems. And so transforming means that my system will behave as expected, and you can have a very trustworthy system, and this may cost a lot of money. Okay, it's developed. So in addition to that, we have engineers have what I call here optimization requirements. And optimization requirements are constraints on the way the resources of the system are used. And you have two types of optimization requirements. You have performance requirements. So performance requirements characterize how the system performs with respect to all its possible users, so throughput, jitter, latency. And you have also cost requirements. And you easily understand that what is important is trade-off between the performance and cost. That is how to get the best possible performance at minimal cost. Okay? And this is a hard problem. Now, just to clarify these concepts that are very important, trustworthiness characterizes what I call qualitative correctness of systems. So, system states may be trustworthy or not. So, if this is, say, very abstract, this is the state space of the system. The red states are not trustworthy states. So, when you design the system, the designer should keep its behavior in this green area, okay? And optimization requirements characterize execution sequences. So when you optimize the behavior of the system, you try to keep its trajectory, its traces, its execution sequences in, to steer the behavior of the system so that, for instance, energy consumption is minimal or something like that. I mean, memory consumption or whatever is minimal. And usually there is two types of requirements are often conflicting. If you want to have very trustworthy systems, then you will need a lot of resources, a lot of money to do that, and you probably know how you can improve trustworthiness of systems by using redundancy techniques, error correcting codes, or whatever. Okay? So, when you design a system, you should find good compromises between trustworthiness and optimization. And this also leads to a distinction that is very common in systems engineering. We have what people call levels of criticality. Of course, we cannot build completely flawless systems, but we have a very critical system, so either safety critical systems or security critical systems, and on the other hand, as I have explained, we have best effort systems. And in the middle, we can make other distinctions. For instance, what people call mission critical systems. So mission critical systems means that the system is available for mission. Typically on the telecommunication infrastructure, data centers, or rockets are mission critical systems. So here the probability of failure is very low. It should be, for critical systems, the probability of failure should be less than 10 to the minus 9 failures per hour. Okay? But when you go here, you have this probability is multiplied by 1,000. Okay, so a rocket is 1,000 times less safe than a civilian aircraft. Okay, and another important fact is that we know that systems have failures, and Of course, in many cases, I think that in media they don't talk so much unless there is a crash of an aircraft okay, but we know, for instance, that in banking applications, banks have a lot of problems onto security issues of systems. Also, we heard probably about this, many problems in cars, many problems in medical devices. So, there is possibility of improvement of the state of the art, and for this we need research. And something else I would like to say is that when you try to build complex systems that are really trustworthy, then the costs, the development costs explode. And this is so there is this is a law. It's called Augustin's law, and it's an empirical law that shows that as complexity increases, the costs, the development, the design costs increase exponentially. And if this law is confirmed, you see this is a graphic that comes from DARPA. This is the agency that is funding mainly military research in the US. And you see that if this law is confirmed, the defense budget, the core defense budget of the US will suffice for the development of an aircraft. Okay, and this is expected to happen something in the year 2050. Okay, now let's say a few words about standard practice today. How we build systems today? We build systems, as I said, in an empirical manner. And then we have some verification or validation techniques. So we try either to verify formally or to do some testing and make sure that the system will be working correctly. So we have no theory today. And as I have worked on formal verification, I got a tournament work for that, I'd like to comment on this. So what is a verification method? A verification method is, this box here takes two inputs, the requirements of the model, and can say whether the model of the system to be verified meets the requirements. And I'd like to make a few comments about that. So if you want to apply formal verification techniques, I don't know how familiar we are with the topic, we have to formalize the requirements. We have to express the requirements in some logic, for instance. And of course, because we want that the requirements be treated by some machine. So usually we are using logic, and the requirements should be consistent. And you know that for large systems, the requirements are expressed initially, say, in English, some natural language. So you have books of requirements, and you have to translate it into, and this is a non-trivial task, translate natural requirements from written in a natural language into formalized. But once you formalize the requirements, they should be consistent. So consistency means that you are not requiring A and not A. I mean, it may sound a bit strange, but perhaps you require A in page 20, and in page 300 we require not A. Okay. And also requirements should be complete. So consistency, we have some theory to check this. On the contrary, completeness, there is no, it means that you don't forget, for instance, you have to specify, give requirements for a lift, okay? So you will say when the lift is moving, the door should be closed, okay? And you give sentences like that. You should be sure that you don't forget any essential problem, any essential requirement. There is no criterion to stop this enumeration of requirements. On the other hand, the model will represent your system at some level of abstraction. And one requirement is that the model should be faithful.